Uh, Today we will be discussing Kepler's laws of planetary motion, and we will definitely be the statements are already you have already studied in your school level, and if we don't have not yet prepared it, I would like to suggest you to go through my notes and prepare the statements for Kepler's laws of planetary motion. There are three laws: first law, second law, and third law. So basically, here we will be discussing Kepler's second law. So this is a derivation of Kepler's second law of planetary motion. So let us first of all check the statement. What does Kepler's second law for planetary motion says? So it states that the radius vector drawn from the sun to the planet sweeps equal areas in equal intervals of time. That is, in short, we can say that the aerial velocity of the planet remains constant. This is the shortest statement possible for the second law. So as from the first law of given by Kepler for planetary motion, it says that every planet moves in an elliptical orbit with the sun as at one of its foci. So suppose it's an elliptical orbit and the sun can have, these are the foci possible. This is say F1 and this is F2. The sun can be at any one of the, so the planet goes round the sun, okay, by keeping it at one of its foci. So what is the aerial velocity constant concept? So aerial velocity means area swept by the radius vector, okay, per unit time. So when I say the radius vector, it is nothing but the vector connecting the sun to the planet, okay. So if this is a sun, so this is the radius vector. If this is the position of the sun, say the planet is now here, so this is the radius vector. So I would like to tell you a much more clear picture about that. So let me draw a diagram to just make it clear. Suppose this is the elliptical diagram, may not be that perfect. So this is, and say this is the position of sun. This is the position of sun. All right. And say this is our blue planet. So it was initially here, it is going there, okay. So suppose that this is the distance it has covered in time t, okay. The planet is moving like this. So now the radius vector is this, and the radius vector has covered this much space. So this is the area covered in time t. So now let us consider some another time. Say now the planet is here, okay, and the planet is going like this in this direction, and now it is here, and this much distance it has covered in similar time, same time t. Okay, so this is the radius vector, and after time t it is coming to this position. Okay, so this is the area covered by the radius vector in time d on this side. So this area, this purple colored area and the blue colored area should be same. So if I name it as A1 and if I name it as A2, so this is the area. A1 is the area covered in time t and A2 is the area covered in time t. So A1, according to Kepler's second law of planetary motion, A1 should be equal to A2. This is the concept. Now we need to prove it mathematically. So for that we will take the help of all the vector algebra that we have learned and in the first unit of our syllabus. So let us go back to that. So we will start proof. We will start the proof. Okay, how to do that? So we will start with the Newton's law of gravitation. So we know that Newton's law of gravitation is given by. So my suggestion is that whenever you are following the video, you should also keep a rough pen and paper so that you can carry the calculation along with me to be just clear your concepts. Is given by. So I am writing in the vector form, so everyone knows it. We have already studied it in our class as well as in our school level syllabus. So let it be our equation number 1. So it is G capital M small m r divided by r square into r cap, where we must mention what is capital M. So capital M is the mass of the sun. So in exam, some students will not write what is capital M, what is small m. So that is a big negative point. Whenever you are using some symbols, you must mention it or define them. Mass of the small m is the mass of the planet. Okay, and small r is the, so small r I am writing in not in vector, it is in scalar form. Distance between the sun and the planet. So therefore one implies, so we have F on this side. So Newton's second law of motion says that force is equal to mass into acceleration. So I can simply, in place of force, I can write mass into acceleration vector, and again it is capital M small m r square into r cap, and then small m, a is nothing but, a vector is nothing but rate of change of velocity with respect to time. So again I am writing everything in vector form, be careful about that. So this is r cap. So can we just eliminate small m and small m on both sides? So here what we should mention, that we have put F equal to m into a vector. Okay, so finally I can write dv vector dt g capital M by r square into r cap. But you know that, so I will be using this as a rough space. So all of you know that if I write r vector is nothing but modulus of r into r cap. R cap is a unit vector along r vector. So if I want to write r cap, can I write r vector divided by r modulus? So therefore I will use this thing in this statement. So therefore G capital M by r square. In place of r cap I am writing r vector divided by r. So it goes to Gm by r cube into r vector. So this is dv vector by dt. So let us mark it as equation number. So this is equation number 1. Let it be, this is equation number 2. And this is our equation number 3. So now moving forward. Now what I will be doing, now equation number 2, you check this thing. I will take cross product on both the sides. So now I'm taking cross product with r vector on both sides of 3 we have. So it is r vector cross dv vector dt, then capital G capital M by r cube. So r vector cross r vector. Now you know that this thing r cross r, so cross product of the similar vector, same vector. So angle theta will be equal to, in this case angle theta will be equal to 0. So sin theta will be equal to 0. This whole term will be equal to then 0. Therefore r vector cross dv vector dt is equal to 0. What should we write? R cross r is equal to 0, since r cross r is equal to 0. Now this statement we need to make a transition. For this I would like to tell you, so there is a rough space again. We will use a rough space again. Let me use some other color. Okay, fine. So in this rough space what we will be doing, say you have r cross v. Okay, so if I take d dt of r cross v, will it go like this? First of all I will differentiate dr dt cross v plus r cross dv by dt. Is that okay? Now you can see that. So I'm changing it, taking just a transition. So dr dt is nothing but velocity. Velocity cross velocity will again be equal to 0. So that means this is v cross v plus r cross dv dt. So this is nothing but 0 plus r cross dv dt. So that means it's simply r cross dv vector by dt. So in place of r cross dv dt, can I write d dt r cross v? So just I am replacing this thing by this thing. So here we will have, implies d dt of r vector cross v vector is equal to 0. So variation of something is equal to 0, or differentiation of difference, this is differentiation of something is equal to 0. That means that something will be constant. So therefore we can write R cross V is equal to constant. Let it be our equation number 4. It's a very important statement. We will be using it further. Now, if I want to represent the planetary motion, so this is the sun, or the planet is here, P, and the planet moves like this. Okay, so this is the position of the next position of the planet, and this position is taken in time delta t. Okay, so this is the first radius vector, and this is a radius vector after some time. If I call this radius vector r, and this is because this is an elliptical orbit, so radius vector will not be same, it will keep on changing. It will, if it is r here, it will be r plus dr here. If it is r plus dr here, it will be r here. Okay, so it is, the radius vector is not going to be the same. So what we have done here, so what I will call, say this is now r plus dr. So this portion will be simply dr vector. So instead of considering it as an arc, I can consider it as a straight line. So if this is a triangle, so it appears to you like a triangle. So if you remember, we had a parallelogram. In the unit 1 we have already discussed the area of a parallelogram. It was the cross products of the adjacent sides of the parallelogram. So it was something like A cross B, if you remember. But you know that whenever you have a parallelogram, half of it is a triangle. So if I ask you, area of a parallelogram is this, A cross B. So area of a triangle will be half of this thing. So it will be half of A cross B. So therefore in this case we will consider the adjacent sides as half r cross dr. Okay, it comes from the concept of area of a parallelogram. So here you can see that so I will call it, since this is the area covered in time del t, so I will call it as del A. Okay, therefore area swept per unit time is del A by del T. So it is half r cross dr by del T. Okay. So instead of considering this as, I will consider it as del r. Okay, so it is del r. Right, so this will be our del r. Right. Therefore, aerial velocity of the planet is, we will denote it as small h. So small h, aerial velocity means vector. So it goes as limit delta t tends to 0. Okay, and it will be, so since area is a vector quantity, so we will denote it as a del A vector. So it is del A vector by del T. Okay, so it is goes to limit del T tends to 0. So it will be half r cross stellar by del T so implies limit del T tends to 0 half r vector cross del r vector by del T. So that is nothing but half r cross dr by dt. So if you can go back to our equation, you can see it is r cross v equal to constant. So here half dr by dt is nothing but velocity. So it is r cross v. So this is the aerial velocity vector. Okay, so this is one of the forms. Say question number 5. Therefore h cross equal to constant from 4 because r cross v is equal to constant. So here we have half into constant. Half into constant means constant. So h is equal to constant, which is nothing but the aerial velocity. So it is proved that the aerial velocity of a planet remains constant. That's it.